Well, how do we arrange electrons in an atom or an ion? So to do so, we need to understand two principles. Pauli exclusion principle, which states that in any given orbital you cannot have more than 2 electrons. So if that is my orbital, I can have a maximum of 2 electrons only. That's what Pauli exclusion principle states. And these 2 electrons have opposite spin, right? And then the second principle is Aufbau principle, which states that electrons always tend to occupy atomic orbitals with the lowest energy first, followed by those with greater energy. In other words, electrons tend to enter orbitals that are closer to the nucleus, which have lower energy, followed by those further apart from the nucleus, which have greater energy. So let's try to draw all the orbitals in a given subshell and try to arrange electrons by taking an example. So let's say this is my shell number n, the principal quantum number. This is the first shell really close to the nucleus, and we know the subshell, there's only one subshell, 1s, and it has one orbital, and it can have a maximum of 2 electrons. Similarly, if I have my second shell, I can have 2 subshells, 2s, 2p, and a 2s can accommodate a maximum of 2 electrons, and 2p can take up to 6 electrons. It could be less than 6, but it cannot be more than 6. And let's say this is the third shell. So I'll have 3 subshells, 3s, 3p, 3d, and 3s can have 2 electrons, 3p can have 6, 3d can have 10 electrons. Similarly, if I have my fourth shell, I can have 4 subshells, 4s, 4p, 4d, and 4f. So S is always 2 electrons, P is 6, D is 10, F can have a maximum of 14 electrons. And similarly, if I say the fifth shell, I can have 5S, 2, 5P6, 5D10, and 5F14. Similarly, I can have, when n equal to 6, okay, 6s2, 6p6, 6d10. Well, I'm not going further because, well, the IB won't assess you further beyond this, and you got to know only until the F subshell. So now let's say, how do you fill up these electrons in a given atom? So this is the order of increasing energy according to the Aufbau principle, right? So let me draw these arrows diagonally, and we simply follow these arrows when we fill the electrons in an atom or an ion. So the first electrons that are filled are 1s. So once the 1s is completely filled, then we try to fill 2s. So 1s followed by 2s. So once the 2s subshell is completely filled, then basically we move up to 2p. So followed by, after 2p is completely filled, we move on to 3s. And after 3s, it would be 3p. Now you must be wondering what comes after 3p. Well, chemists have found out that after filling 3p completely, the next electron goes into 4s basically. Now why is that? Because filling 4s, it's easier for 4s to become stable by just gaining 1 or 2 electrons, whereas 3d has to gain at least 5 or 10 electrons to become stable. So the reason why we fill 4s before 3d is for matters of stability. 4s attains stability faster by just taking 1 or 2 electrons than 3d. So 4s is filled first. So once your 4s is completely filled, then we try to fill the 3d, and after 3d we fill 4p followed by 5s, and after 5s we fill 4d, and after 4d we fill 5p and then 6s. And once you're filled with 6, after you're done with 6s, you can go all the way until 4f. So you fill 6s and then you fill 4f, and after 4f we fill 5d followed by 6p6. Okay, that's 6p. So this is the order of filling or arranging electrons in an atom or an ion. So let's take an example of let's say I have iron 26 55.85. So there are 26 electrons in iron, and let's see how we can arrange these 26 electrons in different orbitals. So following this rule, the first electrons will occupy the 1s subshell or the 1s orbital, so 1s2. So once that is completely filled, then the next electron goes to 2s2. We simply follow these arrows, okay? Start from the blunt end of this arrow and go all the way until the pointed end of the arrow. So after 1s you have 2s, followed by, after 2s we try to fill 2p. Well, you can put a comma after 2p or before that. Then once 2p is filled, we fill 3s2, followed by, what comes after 3s2 is 3p6. Once we fill 3p6, we fill 4s2. You know, we said 4s, it's easier for 4s to become stable by just taking 1 or 2 electrons. That's why 4s subshell is filled first for matters of stability. So far we have filled, that's 4, 10, 12, 6, 18 to 20. So we have 6 more electrons remaining. So the remaining 6 electrons will enter the 3D subshell. So that is the electron configuration of iron 26 with 26 electrons in SPDF notation. So now you must be wondering, how many valence electrons are there in iron? Well, we have to include these electrons, as these are counted as the valence electron. So 4s2, 3d6, so they're all together 8 valence electrons. So let's say, what would be the electron configuration of iron 2 plus ion? So if you're wondering, so if you look at the same configuration, which electrons would be lost? Well, the outermost electrons are basically in the 4th shell, right? So these electrons would be lost first, followed by 3d. So every time you have a d block element ion or a transition metal ion, it's always the 4s electrons that are lost, followed by 3d. So let's write the electron configuration of iron 2 plus. So that would be 1s2, 2s2, 2p6, followed by 3s2, 3p6. So as I said, the 4s2 electrons are lost here. So double positive charge means the 2 electrons that are lost are from the 4s subshell. So it will be, since the 2 electrons from 4s are lost, so that would be 3d6. So this is the electron configuration of iron 2 plus ion.